Today, Wednesday the 27th, we did not have a Zoom session. We will have a Zoom session at our regular time on Thursday at our 9 o'clock in the morning there. You're going to be able to access the link just as usual. Today, I was not able to make it to our Zoom session. So, I'm going to take us here into our Unit 2 charge. I want to point out the calendar that we're working with and what we've been working towards. So you should have started your rocket on Monday doing the steps 1, 2, and 3. Yesterday we started our sticky tape lab and it should have gotten done with that. I'm going to try to show you a little bit more going forward. What I'm going to show you today is a way to get started here with this Explore Charge. Tomorrow during our Zoom session at 9 o'clock, I'm going to show us how to do this explain charge where we're going to develop Coulomb's law and calculate some force. And then we're going to look at the difference between charge versus gravity. And we're going to look at the difference between those two forces. We're going to relate Coulomb's law to the Newton's universal law of gravitation. Going back into our Unit 2, we have this charge, question number 2. So I'm asking that you please get to this. I know normally during the Zoom session I say, please answer charge question number 2. So, please answer charge question number 2, where we have this negative rod, and we have sphere S and sphere R. One is positively charged, one is negatively charged, or they're both positive or both negative. I want you to tell me if sphere R is positive or if sphere R is negative. Tell me if sphere S is positive, if sphere S is negatively charged. We're looking for that net charge on sphere S and R. So once you get that into charge question number 2, that's good for that part. So yesterday we worked on this sticky tape lab. As we worked on this sticky tape lab, we were asked to make a copy and look at some data. So I wanted to show you some of that data that I was having and I was putting together. So when I made my copy of my sticky tape data to insert as my image, I tried to show with the forces when they were attracting one another and the forces when they were repelling one another. And I saw with that top tape a big repulsion, so I changed the force to make that. And I saw a big attraction with the top and bottom tape. And then we went through and did some of that analysis. In that analysis, we were asked to include some hand drawings. So the hand drawings in that analysis, I show here the top tape getting that positive charge and that bottom tape getting the negative charge. We know the top tape had the positive charge because it was attracted to the PVC rod, which is a negatively charged object. Opposites attract. So we know that this has to be positive because it was attracted to a negative. The bottom tape was repelled by the PVC rod, which is a negative charge. So therefore we know opposites attract, like charges repel. So then this negative charge has to be assigned to this bottom tape because it repelled from the negative charge. Then we were asked to draw in for the tape and the paper. So what I drew here is the top tape getting that positive charge. And I tried to draw off to the side here what a regular atom is and the circle around it being the electron cloud. So I tried to draw the top tape with the positive charges, repelling the positive charge in the atom, but attracting more of the electron in that electron cloud closer to that top tape. And then I tried to show it through the tape, showing that the strongest intensity is where it's closest to that the net charge. Similarly, with the bottom tape, which is a negative charge, it's going to attract in the positive part of the atom for the paper and repel the negative part of the atom for the paper. The difference between the paper and the foil is that the paper has these free, or rather, the foil has free electrons. And so when I draw in the foil atom, I draw in the positive part of the atom and the negative part of the atom. And I drew in some arrows here to indicate that this electron is free. It's free to move about. So when I draw the foil here in the middle, I drew this foil. This is without any charges or without anything brought near it. So there would be a positive and a negative, and a positive, negative, then positive, negative, forming this lattice here, or this structure where I could go down, positive, negative, or go to the right, positive, negative, and then go down, positive, negative, positive, negative. And so we see this structure here that would come about. Now, with this free electron, this electron could come down over here, and this electron could go back up over here. What we're seeing with these free electrons is that, yes, in general, we're going to see that this net charge in a localized region is still going to be 0. Positive plus a negative adds up to 0. But when we bring in a charge carrier like this tape, the positive part of the tape, it's going to attract those negative charges that are up here. So leaving this region now at the top of this foil to have this localized region is now going to have some charge to it, because the negative charges are attracted to the top tape. Now this isn't touching, so these negative charges aren't leaving the foil. So in general, the foil still has a net charge of 0. But in this region, there's a negative charge. And in this region, there's a positive charge. Then I can look at the bottom tape. Just a moment, sweetie. No, just a moment, okay? Just a moment. Now with this bottom tape, I see a negative charge. That negative charge is going to repel the negative charges in the foil. Those negative charges in the foil are going to move up in this foil, and the charge carriers, which are the electrons in this foil, those charge carriers, they move from this region to this region, thereby polarizing this region, or polarizing the entire foil, because we brought a charge near it. Now, when we brought these charges near it, that's what's going to help lead us to what we're looking at here today with a soda can. So we're seeing that this polarization occurs because a net charge was brought close to a material. This material has electrons that are free and able to move about. So that's going to take us over here to our today's experiment, or today's assignment of explore charge. So you can see we have this explore charge. So I'm going to go back over here. I'm going to click on my assignment, explore charge. I'm going to click here to make a copy of it. And then after I make my copy, this is what comes up. So in this video, you can watch this. I have a video of someone moving a soda can with a balloon. You can go on YouTube, you can find a lot of videos. I chose this video because they do it and they don't explain it. There's a lot of people who do this and then try to explain it, and then they do the experiment with the balloon on the faucet and they always butcher it. They always mess it up and they're always incorrect. They say then that it has to do with pushing the charges in the water molecule, moving water around, but that's not exactly correct. So what we're being asked is, how does a balloon move a can without touching it? And what factors affect its speed? So I have for us these things I want us to look at. So there's this video getting into these electrostatic forces. You can look at that, and this will help give us some information. All I want you to try to do is record some information here that's going to allow you to help explain why a soda can was moving even though it wasn't being touched. And now I don't want you just to try to say, well, it was rolling down a hill. Well, no, I want it to have to do with a level surface where the gravitational potential does not change. Therefore, there has to be an external force. If a motion of an object changes, that means there has to be a force. So you can get into that video. What I'm going to look at here is this simulation. I'm going to look at this Coulomb's law simulation. So as I click on this and open it up, you can see that this simulation, you can look at the atomic scale or the macro scale. This is dealing with a lot of charges. This is dealing with down to the atomic level. Gets to the same type of scenario, to where I can bring these charges close to one another, and I see I have this big force. And as I get much closer, I get a much bigger force. If I take this distance and I double it, I see that the force decreases by a factor If I take this distance and I double it even more, I see it decreases. If I take this distance and I double it, I see it decreases. I can take this distance and I can decrease it as well by a factor of a third. And we can see that there's a relationship here with the force and the distance, to where the force gets much smaller when it's farther away. We can also see with respect to opposite charges and like charges. So I can move my charge 1 and make it now a positive charge. And charge 2 I can keep as a positive charge, and I can increase the magnitude of both of them to the maximum, thereby allowing me to see what these forces are. So now that I've seen that charge 1 and charge 2, both as positive charges, they repel one another. I can then say, well, now with opposite charges, I see how they attract one another. And the level of attraction, the number here, 2.56 times 10 to the negative 5, is the same as 2.56 times 10 to the negative 5. So I can have it to where it's the same number of charge, a negative 10 or a positive 10, but it just changes the direction. So now I have some information that I can type into here, talking about this relationship between the charge, whether it's positive or negative, and then the other one's positive or negative, so whether or not these charges are the same charge or a different charge, and then the distance between the two. And that gets into some good information. Then there's this reading down here. I really want you to get into this reading. So there's this reading here. You can look through this. This gets into some charges and what you can use for charge. And I don't want you to spend too much time reading, because I know, well, that's not that enjoyable. So you have that level right there. And some of you want to feel like you're in high school again. This is a more appropriate level reading. I think that this is the level where I would enjoy actually reading if I was in high school. So that way I could get really an understanding of really what's going on. And I can start talking about this thing called positive ions, looking at these charge carriers. And this really gets into a good idea talking about this repulsion and no attraction, and then with this attraction. It gets into looking at these charges on objects and what happens to stuff that has these charges on objects. So you can read at a level where it's a little bit easier to read, and then you can read at a level that's more high school. I also have this simulation down here. So in this simulation, I want you to use this static electricity to try to really get an understanding of what's going on. And I have here this sweater and a wall. I can take this balloon, I can move it about. If I try to stick it on this wall, and then I remove the wall, add the wall in, nothing really happens. I can take then this balloon and I can rub it on the sweater and then release this balloon, and I see something happens. What I see happening is I see a charge distribution. So I can show no charges or show just the charge difference. So when I click on the show the charge difference, this is just going to show the net charge. Right now the balloon has a net charge of 0, the sweater has a net charge of 0, and the wall has a net charge of 0. If I take the balloon and I rub it on a sweater, it takes the electrons from that sweater and adds it to the balloon. And then what happens is those electrons that are on this balloon, they get stuck on the balloon. When I let go of the balloon then is attracted to the sweater. And it's attracted because, well, opposite charges attract. I can then take this and then move it to the wall. When I show all the charges, you can see what's actually happening here on the wall. That the negative charges in the wall are repelled, leaving these positive charges on this wall to now be attracted to these negative charges, causing this balloon to stay on this wall. So some of you may have done this. This is what I used to do for birthday parties. I used to just blow up a balloon, I would rub the sweater on or instead of rubbing the balloon on the sweater, I'd rub it on my brother's hair. So that way his hair would always stick up. And then I could stick the balloon onto the wall, and what happens is that negative charges get repelled, positive charges remain, and these negative charges in the balloon are now attracted to this. So this wall allows for the balloon to stay up because it applies a force. If there's a force, that means the motion could change. Right now the net force is 0 because there's no motion. But if I remove the wall, there's a net force again. There's a net force coming from the sweater. If there's a net force, we see this net force because there's a change in the motion where the balloon was sitting still on the wall, and then I remove the wall, and then the balloon starts to move. You can see the same thing happen when you have two balloons. If I take one of these balloons, I can have it gain some negative charge, stick it up on the wall. I can take this other balloon, have it gain some negative charge, and stick it up on the wall. And then you can move the balloons with another one of the balloons. And it's not just specific to just the one, but both of these balloons then will have that same property. So you have something that you can use for that simulation. Now, I just wanted you to write down some stuff here just to organize your thoughts, to help you explain why that soda can was able to move. As I bring this down here, this is where you have this Google drawing embedded into this document. And what I want you to do is just use this Google drawing and explain why that can was able to move. So you got to take these positive charges, these negative charges, and I want you to place them where you see fit onto this drawing, and then add in this text saying, give an explanation of why that can moves, and then you can take this text, you can move it, you can position it however you want to position it, and then I want you to also delete this text and explain why you moved the positive where you did and the negatives where you did. So you can cite your references. You can cite the references such as this balloon simulation. You can cite your references such as this article that we were reading up. You can also cite your references regarding the article and the video. So you can look up, you can use that information there. Once you're done with this, you can take note of the grading down here. I'm not doing a Padlet response, but you can take note of the criteria down at the bottom for how this will be graded up. Once you're done with this, you can go ahead and turn this assignment in onto Schoology, and we're going to have our regular assigned Zoom session tomorrow at our regular time. So thank you very much, and have a great day now.